many features in the Matlab, so many functions that gives us a wide range of diversity to deal with the with the design of the feed-forward ANN. So we need to know the details of all those facilities and the functions that Matlab support for its use in a diverse range of domains. So we will be focusing primarily on a detailed a review of the training types that a feed-forward structure of the ANN can use, and then consider it for a variety of purposes. So the basic plan of presentation shall be like a brief focus on the different training types of gradient descent, then types of training, then a few examples. So this particular diagram is the basis of how the Matlab compiler's logic is formulated while designing a feed-forward a neural network. So it is a feed-forward neural network. So here there will be an input, a hidden, and an output layer. And then there shall be one 10 sigmoidal function and one purely linear function. So the 10 sigmoidal activation function will be in the hidden layer, and a linear activation shall be in the output layer. So these two types of activation function normally is considered to be the default in the Matlab training built-in functions. So these are the most common types of activation functions that Matlab will be considering while designing the neurocomputing structures. The linear one, the sigmoidal, and the 10 sigmoidal activation functions. So in the linear case, we will have a straight line. So the straight line will be discriminating the classes, and that shall be quite sufficient for dealing with simplistic classifications. The sigmoidal function will be required for multi-class classification while we confine the classification decision codes between 0 and 1, while the 10 sigmoidal function is quite relevant while we deal with multi-class problems, but confined between -1 and 1. The decision logic confined between -1 and 1. And so these three have their own strong points and drawbacks. Linear activation will be preferred where polarity is not a consideration. Then sigmoidal activation is taken into consideration when we are dealing with unipolar or one type of polarity in the classification decision, and when we are facing bipolar codification or bipolar classification codes, we need to use the sigmoidal activation function. So now, last time we saw how to create a simple feed-forward ANN with the Matlab. We used the new FF function, and there we have spoken about how to create the different layers, how the min-max function is used to get the range of values, the range of minimum and the maximum values that the vectors will be carrying, then the number of layers in the hidden layer, and a number of neuron in the output layer. So we have considered about that. We have further spoken about what is the significance of the tensig function and the Piolin function. Then we have spoken further regarding the train GD function. That is the batch training with gradient descent. So this is the most common or the default training method that Matlab will use while designing a feed-forward neural network. Now, now there are several forms of the gradient descent function that is used in the Matlab. So here we find that this particular syntax will be creating a neural network object or structure and will initialize the weights and biases of the network. And this network is now ready for training. So here we can use this NIT net function to initialize the value, the weights. Then while we want to simulate the network, we can use the built-in function sim. So here is one such way. So if we use the vector p1 and 2, and we have defined some network where the variable net holds the network, then we can use sim and then pass the vector p to simulate the network's response. Here A gives us that particular response. Now we further last time have considered that if we take P and T to be two different targets, to be the pattern and the targets, P is the pattern and the T is the target, then we can use the min-max function to find out the range of values that both P and T that both the vectors of P are supposed to give to the network. So min-max function will be giving the minimum and the maximum value ranges for this particular vector. Then 3 and 1 will be the number of neurons in the middle and the back end layers of the network. And tensig and Piolin we have been familiar with. So then further there are a few more parameters while we that we need to define while we train the network. One is the so parameter, means display once in the gaps of 50 number of iterations. The learning rate is 0.5, number of iterations or the epochs, that is 300, and the training parameter goal, that the mean square error value must be converging to this 10 to the power minus 5 value. So this is the training goal. So this particular training goal will be the MSE goal that the network must give while the training is on. Now this particular method is the batch training method, where all the patterns and the targets are fed to the network in one go, and then in one cycle once we complete each of the cycles, the weights are tuned, the weights are varied. Okay, so here is the display that we will have while the training is on, and at some point of time when the MSE goal is met by this train GD function, that will be displayed like this, and then we can we can generate the response from the network by the use of this sim function. So simulate the network's response by the use of the trained network and feeding it with the P pattern vector will retain or will return the values as shown or as returned or as stored in the variable A. So these are the values that are generated by the trained network when we feed it with the pattern vector P. Now, we have last time spoken about that there are two types of training, two broad classes of training that we see in the case of neural networks. One is the batch training, and next is the sequential training. Batch training is the more common form of training, and here the most uh, rudimentary form of training is the batch gradient descent, that is called the train GD. Now, here in this train GD, there are several parameters that we need to define with or need to deal with. These are the epochs, so goal, time, minimum gradient, maximum fail, that is the maximum fail limit, and the learning rate. So here the learning rate parameter is a very significant one. We will speak about the learning rate quite frequently in the subsequent slides. We need to remember that the learning rate must be fixed in such a manner that the tasks of the network learning is fulfilled well. So if we have a very large learning rate, the network may not be that stable, and if the learning rate is too small, we will find that the algorithm might take a long time to converge. So these considerations must be taken into the calculation while we fix the learning rate. Now, there is one more type of the batch gradient descent function, that is called the train GDM. That is one more type. So now here we find that the gradient descent comes with a momentum term. So this particular momentum term makes the uh, makes the the MSE conversions faster. So here the momentum term guarantees that the network will respond to local gradient variations. So the momentum term will function like a low pass filter, and the term momentum term further permits the network to round off small variations there in the feature. Now, the use of this momentum term prevents the formation of the local minima problem. So the train GDM is a developed version of the train GD, where the momentum term permits faster conversions, greater reliability, and it further prevents the formation of the local minima problem with a with an ANN. So this is one of the better versions of the gradient descent function, gradient descent training. So here is one such training. How we will do. Most of the things are similar, but the function here is changing. That is train GDM. So this is a built-in function. We can write like GDM. Previously, we have written it train GD. Now we are writing here train GDM. You might recall that in the previous case, the number of epochs required there were about 273, but now you see it is coming down to 114. So we find here in the very first glance that the train GDM has a faster convergence of the MSE value. So it is a better means of training the network. So this trains the network better. It prevents the formation of the local minima problem, and therefore has a faster convergence. So So this is a better version of the batch gradient descent training. So now these two were the train GD and the train GDM. Yes, yes. And please don't mind. The power had gone, and then power is again coming back. So we will continue. So there are faster means of training. So the previous ones are the more common versions. So train GD and GDM, these are the more common versions, but they are comparatively slower. So they train with lesser convergence rates. Therefore, there are two more classes of faster training. One is called heuristic training technique, and the second one is called the numerical optimization technique. Now, in the first one, there is one training rate called the train GDA, where the learning rate is varying, or where the learning rate shall be varying. And the second one is called the resilient back propagation, or called the train RP. So these two are faster training methods. And then in the second class, that is the numerical optimization technique, we have a class of conjugate gradient functions that will have train CGF, train CGP, train CGB, and train SCG. And in the second class, second category, that is the quasi-Newton category, where you have the train BFG, the train OSS, and the Leavenworth Marquardt, or a train LM. So these are considered to be the faster training methods. Now, train GDA is a variation. Train GDA is considered to be a landmark. Now, before train GDA came, where train GD and train GDM were the standard methods of the ANN training, there we found that the learning rates are all fixed constant, or are held constant. So we have spoken about
Sorry,
that.
sorry, sir, may I
Hello?
interrupt?
Hello?
We can't see the screen.
Yes, yes, yes. Okay. Please, wait. Yes, yes, yes. Sorry. Please don't mind. Sorry. Okay. Yes.
No problem, thank you.
Yes. Now the screen is coming.
Yes, I
Yes.
was all
Yes.
right.
Okay. Let's continue. Okay. Now the previous training methods, all the we found that in case of train GD and the GDM, the learning rate was held constant. Then we further came to know that if we have the learning rate set to be is set high, we may have a unstable network generated. And if we fix the learning rate too small, then we will find that the network will take too long for the MSC conversions. Therefore, we can find that the performance of the steepest descent based training can become better while we permit the learning rate to change during the training process. So 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 that means that we have here formulated a technique where the learning rate is made responsive to the complexity of the local training mechanism. So this is the strength of the train GDA, where the learning rate will consider the local variations, and that way the learning rate will be varying. So here is one such training method. Same thing, pattern and targets are defined. Min max function is used to capture the minimum and the maximum values of the pattern. Then finally we have used here train GDA. Same thing again. The convergence goal is fixed at 10 to the power minus 5. Then while we see the training and while we carry out the training, we will find a network structure of this type will be generated. It shows the layers. The front end layers shall be there. Middle layer is here. This 2 will mean a two row vector coming. So here there is a three neuron middle layer and one neuron output layer. This is based on a train GDA function. It goes up to 300 number of iterations. So it has reached a performance goal of 9.99 multiplied by 10 to the power minus 5. So it's quite good. So the training has been carried out. So that way we can check its performance also. So this is a screenshot of the network structure generated during the training part. Similarly, there is one more training type called the train RP, that is the resilient backpropagation. Now this resilient backpropagation prevents the fluctuation in the activation function responses when we use a diversity of activation functions, like we use a combination of log sigmoid and 10 sigmoid functions. So we may sometimes have situations where we want to use both the log sigmoid and the 10 sigmoid functions in combination. There we will see that the magnitude of the responses will be varying. So if they vary, then we will find that the partial derivatives generated during the calculation of the MSE values will be also showing us variations. So the resilient back propagation prevents the detrimental or the side effects of the magnitude variations. So it here makes the network fluctuations less. It will have a smooth training, and it will make the conversions fast. Here we can use the same thing and then replace the training by writing here train RP. So the same goals. We will find here that the training is quite fast. Just 24 number of iterations are taken to reach or to cross the performance goal. So that was set at 10 to the power minus 5. That has crossed 10 to the power minus 6 in, say, 24 number of iterations. It's quite fast because its resilience prevents the fluctuation due to the variations generated for the use of 10 sigmoid or log sigmoid functions. Now there are one more set of training functions that are regarded to be fast. These are called the conjugate gradient training algorithms. Now the most striking part shall be that the weight search or the learning rate search or the step size search. Now these searches are done in a conjugate form. Conjugate form means you can consider a baseline gradient. You can consider that the gradient is rising or falling. So the next gradient value can be a plus minus value. So this particular search in the positive direction of the gradient or in the negative direction of the gradient shall take place in a conjugate manner, and this particular conjugate search will calculate or will find a value for which the network must guarantee a faster convergence. So here this particular search of finding the parameter values in both sides of the gradient will take place in a conjugate manner, and that particular search, though, is a time consuming process, but guarantees a faster convergence, and step sizes are varied in each of the iteration. So this is a major benefit. This is a plus point, and that guarantees a fast convergence. Now, in this the first of the conjugate gradient functions, there is one method which is due to Fletcher and Reeves, and that particular training method is called train CGF. So this CG means the conjugate gradient, and F due to this Fletcher-Reeves contribution. So while you do the training with this train CFG, we find that the conjugate gradient algorithm start out by searching in the steepest descent direction, negative of the gradient. Then in the first iteration, and subsequently both ways the searches shall be done, and that way the most likely values are considered and taken for doing the gradient descent training. So same thing, but the training function now changes to train CGF. Rest of the values are same, and while we do see the training time network structure, we find that it takes 10 number of iterations to reach the gradient minimum performance value it will cross 10 to the power minus 5. So it will reach the desired convergence limits. So it's quite fast. So we find here that the train CGF is one of the faster training methods. So it's fast. It takes less number of cycles, iterations to reach the goal. Then there is one more type of the conjugate gradient training called the train CGP. Now this P comes from the Polak Rebbe contribution. So here same thing. The train CGP is here considered. This is a variation of the CGF. Here a more normalized form of the gradient descent is considered for doing the search. So here we find that here 7 number of iterations are considered or required to reach the performance goal quite fast compared to the train GD and GDM. Quite fast, very less number of cycles are required to reach the performance goal. So that way we can have a faster means of doing the training. Now, why speed is so much a critical factor? Because of the fact that till these recent gradient descent functions were launched or have come, the neurocomputing training part had faced criticism for the fact that they take lot of time for doing the training. Yes, all types of neural network, all types of ANN take lot of training time. Therefore, faster means of training, faster techniques of training are being proposed and have been developed. Then there is one more form of the conjugate gradient function that is called the Powell-Beal restarts, CGB. So for all the conjugate gradient algorithms, the search direction will be periodically reset to the negative of the gradient. So by following the steps given by this particular method, this method will restart if there is very little orthogonality left between the current gradient and the previous gradient. So it senses the variation of the gradient, and that way will decide or will start from a fresh value. So here it is written as train CGB, and this particular train CGB gives a different feel of the training. Previously we saw that there were 7 number of iterations required. We now find that 6 number of iterations here are required to cross the performance gradient of 10 to the power minus 5. So faster or greater speed is generated. Now the more popular version of the version of the scale gradient function is called the scale conjugate gradient, or train SCG, a very popular function, and it has certain benefit that it gets rid of all the time consuming line searches. So much of the time taken previously in the line searches for different parameters are now skipped or are not required, and it is found to be one of the more popular scale conjugate gradient functions, and these are used more nowadays with the training of the deep neural networks. So rest are same. This function changes, train SCG. So this is a new form of the scale conjugate gradient functions. So here we find that there is a minor rise in the number of iterations taken, but we will see, or in the practice we see that its generalization is much better compared to the rest of the conjugate gradient functions, and its time consuming nature is one of the reasons for its greater popularity. Then there is one more one more training method, and this is based on Newton's on the quasi-Newton's optimization technique, and this is called the train BGF. So here the last part, BFG changes. It's not BGF but BFG changes. So we here find that this particular quasi-Newton training method will take about 9 number of iterations to reach or to cross the convergence goal of 10 to the power minus 5, and generates a stable response. Then a less popular but yet a reliable training method is called the train OSS, one step sectant. So the one step sectant part here is a part of the quasi-Newton sectant algorithm. So in the last part you can write train OSS. So rest of the parameters are same. So it takes about 25 number of iterations to reach the goal, somewhat more time consuming, but it takes lesser memory space, and its generalization properties are better. Now in the Matlab domain, or in the Matlab based ANN training, this one is considered to be the faster and less resource demanding training approach. Levenberg Marquardt and training. So it's quite fast and known to be fast, and it is found to be possessing better generalization characteristics. So it is denoted by this train LM, and is quite popular worldwide. So you can see here it just takes about 2 number of iterations to complete the training and reach the goal of 10 to the power minus 5. So you can see here the convergence curve just takes two steps, 2 number of recursions to come down and reach the goal quite fast, very fast. So for a near real-time performance that we require, we may use this train LM method. So while you complete the training, you may see what is the gradient value at the second number of epoch, then the step size, then the validation checks. So here validation checks are carried out if it touches the required convergence level. So here it is and the depiction from the training time situation, from the training performance of the parameters. We can select an project like this. So it's quite reliable. So it's faster and reliable means of training. So you can further do a regression. That means if we want to give the pattern to the network in a trained state, both the desired values and the generated values, if they coincide, they will lie in a straight line at 45 degrees. So this clearly shows that the learning part is complete. Both the generated response, present response, and a desired response are nearly uh, coinciding in a very short cycle of training. Now we can do a comparison. A comparison is shown by the use of cholesterol data. So if we take cholesterol data, so this part of the data is from the network.com a repository. So they have taken a cholesterol data set of about 5,000 people and have done the training with all these previously talked about training methods, and they have compared the complete complete performance. So we can find here all the parameters that were generated during the training by these different training methods, like the Levenberg Levenberg uh, Mark quadrant, then BFGS quasi-Newton, resilient backpropagation, scale conjugate gradient, then conjugate gradient with Powell-Bill restarts, Fletcher-Powell conjugate gradient, Pollock-Ribéry conjugate gradient, one-step sectant, and variable learning rate backpropagation. And in most of the cases, people find the scale conjugate gradient and Levenberg Mark quadrant methods are the most reliable, popular, faster, and resilient means of training a feed-forward network. Now, now here is a critical case: how we can reinforce the generalization capability of an ANN. So we know that the ANN suffers from training. So if we try to do lot of training with the same data, we find that the network starts to do fitting of the curves perfectly. We find that the boundary demarcation is done with high levels of precision. Further, we find that if we continuously train the network with the same set of data, then we find that it develops a biased nature. Its generalization property suffers. It starts to remember. It develops a memorization capability. Now, this is not desirable. This means that it is losing generalization. Therefore, we need not have perfect fitting. So we need to get rid of this sort of perfect fitting. So now, to help generalization, there are means and methods provided by Matlab that permits the user to design the network that has better performance capability. Now, one of those methods is the quasi-Newton backpropagation BFG. So it has better generalization capability, and therefore, for situations where generalization is one of the requirements, this particular method is preferred. So here is one such depiction. We have used the train BFG method. So we see that here iterations are taken to reach the performance goal of 10 to the power minus 5. We can see further that this is the training convergence graph, uh, crosses the desired limit of 10 to the power minus 5 within the 7 number of epochs, quite satisfactory. Then we can also find the gradient values, the validation checks, and the resets at the end of the seven numbers of training cycles, or 7 number of epochs. So this is one of the methods that will give us better generalization. Now, for better generalization, sometimes people do pre and post processing. So before training, they do a processing, and once we complete the training, we do a post processing. So in the pre and the post processing, we find that there shall be scaling of the values and confining them into certain given ranges, into certain specified ranges. So when we do a scaling beforehand, a pre-processing means we have a lot of values where there are a huge number of variations. So those particular variations now can be scaled up or down and confined within certain given ranges. So that will permit a faster, a speedier convergence with better generalization. Now, once we do a pre-processing, that must be followed up by a post-processing. That should be done once the training part is complete. So now for that, you can use functions like pre-M and MX. So these are used for scaling the values, patterns, and target values within the range -1 and 1. So this will be doing that. So if your patterns and the targets have different values, so their variations give us considerable diversity, for which the computations will rise, for which the resource requirements shall rise, and the training time required shall be rising too. But if we can confine them to given limits, then our training and our resilience, the performance, the requirement of the resources shall be lowered, shall be minimized. Therefore, we need to do pre-processing, and if we do pre-processing, we should be following it up by a post-processing. So one of the steps of doing the pre-processing is to use a function, a built-in function called pre-M and MX. So once we do that, we will get the new set of patterns and the targets. So those will be used for doing the training. Now, once we do the pre-processing, since we know there should be a post-processing, for post-processing, we need to use the pre-M and MX function, which will be doing, say, one more scaling, both the patterns and targets. So here is one such way. So once you complete the simulation or complete the training part and do a simulation to generate the network's response. Now, to get that true response from the network, you need to do a post processing, and for that you use the post M and MX function. Now these two parameters, min t and max t, they are coming from these two values that should be stored beforehand. Okay, so now there are provisions through which you can use both pre and post processing as part of the training. as part of the as part of the uh, training. So there is one function here, trend m and mx, where p new, p min, p and the max p, both these values are given, and then the training will take place and the post processing will take place. So this will guarantee that both pre and post processing are done as part of the training. So the network will now take care of all the requirements of pre and post processing training. Now, there are provisions where we can use certain statistical properties to reinforce parameters. We sometimes want that mean and standard deviation values of samples be used for generating better results. So sometimes people use mean and standard deviation as part of the features. Therefore, this function pre STD, pattern and target, P and T, can be used to generate mean and standard deviation values. So this can be done before the training part, and once the training part is complete, we can generate the response of the network, and that part of the value, the value which the network generates from generates by taking the scale version of the patterns, can be passed through the post std function to generate the mean and standard deviation value removed version of the functions of the values. So mean and standard deviation as part of pre and post processing while doing the training can be used this way. So similarly, we can use both mean and standard deviation as part of the training. So here the train and TRA STD, P new, min P, and the STDP, they are used to generate a new form of the pattern. So it will be used with the train network to generate the the response with mean and standard deviation considered as part of the training. Then once we do that, we have that particular response. We can now remove the contribution, the start contribution of the mean and the standard deviation by the use of the function post std a nu n and min t and std dt. So we can do that, and then before training and post training, we can put and remove the contributions of the mean and standard deviation values, and then have a better means of training of the ANN. Then several times people find that the principal components are considered as part of the ANN training, because principal components are rich in features, and when they are rich in features, they help in better pattern learning. They have greater discrimination capability, so they have superior class, or they give superior classification performance. Therefore, sometimes we can use the principal components as part of the training. So here are some means. So this is the standard deviation. Here is a mean, a function called pre-PCA, through which we can here specify the calculation or selection of PCA values with 2% margin. So this one goes through. Then once you do the training and you simulate the network's response, since we have here done a PCA, or we have here considered the principal components, that way we have restricted or have removed the redundant part from the pattern. Post training, we want all of the contribution of the components. Therefore, we can do a regression. So if we use the pre PCA, we need to use the post regression function to nullify uh, the role of the PCA capture beforehand. So this one will give us a better discrimination performance, a more compact feature representation. If we are not sure what will be the type of features we want to use with one particular case, PCA is a very reliable means of selecting features. So if we want to reinforce the PCA part, and I've used the PCA for doing the classification and discrimination beforehand, before carrying out the training, the reinforcement of the PCA contribution should be nullified by this post REG function, which will smooth off the prominent part of the PCA, and then normalize the, mm, the values generated and the performance. Now let's see how a standard training session will look like. Now, for a standard training session to run, you need to load a data set. So here we have shown that we are loading a data set, and from this data set, we can take supposedly 10 rows for patterns, and then the subsequent part we can take for the target part. So we have here considered the pattern and target coming from the cholesterol data set that is built in the MATLAB package. Now, we from that particular pattern and the target set, here we have done a standard deviation. We have reinforced the standard deviation part before, and so we have used the pre-STD function. So similarly, we have reinforced the PCA part, since we are not sure about the features that will be good for classification of this cholesterol data. Then we want to know the size of the data sets that are generated post pre-PCA. So therefore, we find here the P and Q. Then we take 2 rows and two columns to formulate the specific pattern that we will use for doing the training. So here we use the PTR to be the pattern vector. Similarly, we use the TTR to be the target vector. So once we do that, we now formulate a feed-forward network, which will take the minimum and maximum values row-wise, with 5 number of neurons, 5 number of perceptrons in the middle layer, and 3 number of perceptrons in the uh, output layer. The 5 neurons in the middle layer will be of the 10 sigmoidal type, while the 3 neurons in the output layer will be of the purelin type. And here, since I have said beforehand that train LM is one of the popular means of training, so here it is used for doing the training. Now, this is a detailed means of training, where validation and testing time performance parameters are uh, considered. So once you do that, you can plot the training time uh, and the the training time epoch count, the training time performance, training time epoch, and the validation time performance, training time epoch, and training time uh, performance. So there is the graph. Then we want to see what will be the what will be the result once we complete the training part. We want to see the simulation result part. So we use the train network, feed the patterns, the p trans, that part is the p trans, complete set of features we have fed. Then we have done use the post STD. We have removed the standard deviation reinforcement part, as we have said beforehand, and then have generated the true representation of the values, and then we have plotted it. So we find that roughly around that uh, discrimination line, the types cholesterol types, three types, since there is this class 3. See, there are three classes of cholesterol distributions. They are grouped uh, roughly around that discrimination boundary. So this is how we can run a sample training session. Now we come to a few more training uh, techniques that are part of the latest versions of the Matlab. Roughly, Matlab 19 and Matlab 20 give these functions. These are quite fast. These are all built on VC++ and quite fast, and they give very good reliable performance. So one is called the feedforward net. One is called the configure net. Feedforward net, you do not follow the complications as were seen in the definitions till now. We need not follow all those things. This feedforward net function is quite smart enough. It can create a network and work together with this configure net to formulate the most reliable or the most suitable optimized version of the network to give the best performance. So the feed forward net will create a feed forward ANN, and then the configure net will fix the configuration of the network. So here we can fix a pattern like this. X will be the pattern, T will be the target. So here we can see that plot. Uh, we can use plot function to see the distribution between the pattern and the target beforehand. So we will mark it with this O. So we can here see that the feed forward network is created. Now it is configured. Configured means X and T, they can have different formats. So their lengths will be there. So depending upon the lengths, the network configuration will be created. So the response of the network will come to y1 variable. So we don't here use the sim function. Simply we can write net of x. So this net variable will take the parameter or the pattern vector x and generate the response. So this will be plotted before the training. So once the network is trained, then it is re-simulated. So now that is the way to train, and then re-simulated it, and we can then plot it one more time and then compare both the results before training and after training. So here is some that is the case. That is the case before training. That is the case post training. It's quite closer to what we want, what is desired. 3 number of iterations are taken, and the performance goal is crossed. So these are the values of gradient and the step sizes and the validation checks done. So here is the convergence plot, the mean square error plot. At three sessions, it has crossed the performance limits. So quite fast and quite reliably generated graph. So it's quite the performance is quite satisfactory. Now, once we generate or complete the training, we can do lots of validation checks. We can carry out carry out regression checks with different values. So here we do a regression check by taking a regression coefficient of 1, similarity with the training set of 1. Then we can take, if we do not specify the test and the target values for doing the regression, that will take its own default values. And if we now do a regression check by taking a regression coefficient of 0.98, that is, there are 98% difference in the test set taken, yet the performance we find is very close to what we want. So it's quite a reliable performance. Then Matlab, the later versions support parallel computing. So it's quite beneficial for the researchers to get rid of all those complexities of finding out free CPUs and then running their uh, training. Now here is a case where, as part of the neural network, the NN toolbox, there is a provision for the use of the parallel computing toolbox. Now here is a feed for here is a declaration through which you want to tell the compiler that you will be using the parallel processing toolbox. Normally, our CPU cores, they will have multiple cores. Most of the time, one core is used. Rest of the cores are free. Now, through this parpool function, you are telling the compiler that you now prepare the function for carrying out a parallel processing based training. So here you configure a feed-forward net with 10 number of middle neurons. So it's a big network. Middle layer is quite thick. So you are giving the pattern and the target, then use parallel processing on. So that you are saying yes. So for the use of the parallel processing toolbox, you are giving the primitive yes. Then so resources, you want to display the resources that are used for doing the parallel processing based training. You are saying yes, you display the resources. So once you do this or give this declaration, you are simulating the network. Then it will give a display starting parallel pool using local profile connected to two workers. Now, two workers means you are doing work with two processors, two CPU cores. So here is a display. So this is how you can do a parallel computing based training with the help of the Matlab. It's quite fast. It gives nice performance. So it shows the training the training time display will be like this. So the different parameters showing fluctuations as per the training cycles, different iterations, validation checks. So with different regression counts, the regression plots will show us changes. Then the mean square convergence, the mean square plot depending upon the training cycles can be seen like this, how it converges to reach the performance goal. Then MATLAB supports GPU. Now, many times we find that our present-day computers come with GPU cards, and we do not know how to use the GPUs, because parallel computing is one way. Use of the GPUs shall be one more way to speed up the training and prevent the training latency to catch up. So use of GPUs is permitted in the MATLAB. So say again, here you are defining a GPU array that will be processed. That will be processing the target vector taken from the vinyl data set. This is the pattern created in the GPU. Same way, that is the target pipeline created in the GPU. So you are configuring it, training it, displaying it, or simulating it, gathering the values, and then you are running it with parallel processing and use GPU together, and see. And then once the training part is complete, you are simulating. So it shows us clearly how GPUs and parallel processing can be used together. Then MATLAB sometimes, since we know that sometimes for very critical cases, we need to use a cascade of feed-forward ANNs. We can use the new CF function to create a cascade of forward feed feed-forward backpropagation networks. So here we can use a number of, that will be the pattern vector, that will be the target vector. Here we are creating a cascaded feed-forward network that will be dealing with the pattern and the target vectors with 5 middle layer neurons. So it can be simulated and we can plot the results. Now, in the later versions of the MATLAB, there are dedicated functions. There are dedicated feed-forward ANN functions meant purely for pattern recognition. Meant purely for pattern recognition purposes. So now here is one such network that is meant purely to deal with pattern recognition, pattern net. So now we take a data set, a iris data set built in there in the MATLAB toolbox. Separate out from that the pattern and the targets. We create a pattern net with 10 middle layer neurons, train it, view the network, simulate the network, and then generate the performance and performance plots. And finally, we want to do or check the classification performance, how to check the classification performance or generate the class details. That is the way to generate the class details. So here is the training time depiction, the neural net structure generated. The middle layer will have 10 number of neurons, and the output layer will have three neurons, because there are three classes. So the different variables created during the time of the training is shown there in the workspace. Now while you report the performance and then try to send it to a journal or for a conference, all the graphs that you want to have can be generated from these buttons: performance, training state, the error histogram, then the confusion metrics, so on and so forth. So here is one of the graphs: cross entropy and the best validation check, and convergence plots shown together for different number of training cycles. So both train, validation, and test checks are shown with the best result depicted, or the best performance margin shown as a milestone. Gradients, while the iterations are changing, validation checks. Then quite frequently we need to have the confusion. We need to have the confusion metrics. Now the confusion metrics gives us several things together: true positive, true negative, false positive, false negative, then precision, specificity. There are so many parameters through which you can describe a pattern recognition performance. So all those things are together summed up, or together are reported by the confusion metrics. So here we see a training time confusion metrics generated, a a validation time confusion metrics generated, a confusion metrics generated during the testing time, and a target class all confusion metrics generated. So here these last values: 96.7%, 95.7, 97.1, 95.7 will be denoting the reliability. Now this particular 97.11% will be the training time reliability. 95.7% will be the validation time performance. So testing time performance is 95.7%, and all confusion metrics combined together for the target classes gives a performance count of 96.7%. So this gives us a clear depiction of the performance generated by the train network that is used, or that is configured specially for a particular pattern recognition problem. So here I will be summarizing. So feedforward ANNs are very well designed by the use of the Matlab. There are a wide range of support we can get from the Matlab. Faster methods of training of the ANN are there and are built in as part of the Matlab library. Then we have specialized versions of the ANN's training that can be used and configured for special requirements to suit our purpose. So the range of possibilities of training the ANN with the use of uh, Matlab is nearly limitless, and it gives a edge for checking the performance of the networks and then writing it for journals and so on and so forth. It's a very quick, reliable tool. So before I close, here is the reference, Simon Higgins' book. And before I close, I would like to request you all to raise questions. That shall be great for me to reply. I shall be sharing the slides to you all. I shall pass it to Dr. Kaplan. From him, you can collect it, and once you collect them, you can try and run one or two programs in the Matlab. You will all like it. You will all feel good. And once you try one time, two time, three time, from the fourth time, you will feel that you need to do more. It's so fascinating, and since it's quite forgiving, and it makes the whole thing quite trouble-free for you, for its built-in libraries, built-in functions. So here, learning turns out to be a fun-filled work. Therefore, uh, therefore, you need to do two sessions, or you try and see Matlab, then practice. You will all feel good. Later on, this will give you great lift in your careers. So with this, we come to an end. We'll meet one more time on next Tuesday with a new topic. So thank you to you all. Thank you.